recorded two, right? Is that right?
Okay, welcome back to the online calls inference seminar. The first seminar this quarter will be, or this spring will be quite special because we will have a collaboration with the Isaac Newton Institute. And today we're going to start with two speakers, Yilin Song from Columbia University and Richard Guo from the University of Michigan, who will speak about the categorical instrumental variable model, characterization, partial identification, and statistical inference. As a discussant today, we're excited to have Desiree Kedagny from the University of North Carolina, Chapel Hill. Questions today will be handled by Chingwan. Chingwan, do you want to say a few words?
Yes, of course. I think there's this Q&A button below that you can use to open this tab, and then you can put your questions there. I'll try to stop the speakers from time to time to take questions. Yeah, otherwise, looking forward to the talk.
Okay, let me share screen then. Can everybody see the screen? Okay, cool. Yeah, great. Thanks so much for all the organizers of the online calls seminar, and also thank Professor Kodakny for being our discussant of the talk today. So today, Richard and I are going to be talking about our work on the categorical instrumental variable model, characterization, partial identification, and inference. So this is a joint work with Professor Gary Chen and Professor Thomas Richardson at the University of Washington. In today's talk, we'll first start with motivation, and then I'll discuss our settings, assumptions, and main results for the categorical IV. And then Richard is going to take over and talk through the statistical inference and data analysis of our work. So I'll start with the motivation. Our real data example is coming from this domestic violence experiment, where domestic violence calls are usually one of the most common but also challenging call types of law enforcement. So how police respond to those cases can be quite complicated but also important. How police respond to domestic violence calls has changed substantially in history. So starting with the 1970s, a lot of departments are taking this hands-off approach. So for example, in New York City, arrests are only made in cases of serious violence. And then women's advocacy groups were calling on police to take domestic violence more seriously and change the intervention strategy. So in the 1980s, National Institute of Justice funded this Minneapolis Domestic Violence Experiment, and that is actually one of the most influential randomized experiments in criminal justice policy. So the police will take the domestic violence 911 calls, and both the victim and the offender must be at scene to be included in this study. When an officer believes that a domestic violence case has occurred, they were instructed to take one of these three courses of actions by a lottery system. So they will either arrest the offender, or they will advise and mediate the situation, or they will separate the offender from the victim for 8 hours. And because this is totally determined by a lottery system, this instruction, as you can see, is completely randomized. And of course, then the police can decide the actual action they're going to take. So a total of 314 cases were included in the study, and the suspects' reoffense status were followed up after a 6-month period through self-reports or from a police database. And that is going to be our primary outcome that we're looking at in this study. So here is the result of the experiment. Here we use Z to denote that action instructed by the lottery system. So we have arrest, advise, or separate. And then as I mentioned, what's assigned is not necessarily the same as what the police is going to actually take. So we use the X to denote what is the actual action taken by the police. And again, we have arrest, advise, and separate. And our Y is binary, so either reoffense or not reoffense in a 6-month follow-up. And specifically, we just use blue to denote the number of cases with no reoffense, and then red to denote the number of cases with reoffense. So in these type of studies, there are a couple of analysis that people usually take. So the first one is this intention to treat analysis. So this will be only looking at what's the random action assigned. So that will be only looking at the Z, but not the X. And that will be just looking at the column sums for each of the Z arm. So even though in this case, ITT is a causal estimate, we can identify that. But because this only focus on this randomized Z, and there is much non-compliance in this study, and that is often also context dependent. So that is not necessarily an true efficacy of the intervention itself, just because we focus on the assignment other than the actual action taken. And another analysis is this per protocol analysis. So this only focuses on the cases where the actual action taken is the same as the assignment. So that'll be looking at these 3 selves. And this might not be causal anymore because here this is not randomized. And the cases that comply with the assignment, for example, in this arrest arm, might not be the same as the cases complying with the assignment in the other 2 arms. So in the original study, they found that the offenders assigned to be arrested had lower rates of reoffending than offenders assigned to counseling or temporarily sent away, as you can clearly see just from these 2 types of analysis. So as I described, Z is completely randomized, and it is reasonable to say that it has no effect on reoffense other than through the action taken. And if you're familiar with IV analysis, you can already see that this is a very classic categorical instrumental variable model with both the instrument and the treatment taking 3 levels, and we have a binary Y. So this is a DAG that you would often see from most of the IV paper. So for Z to be a valid IV, it needs to satisfy 3 different assumptions. The first one is independence, that Z does not directly associated with this M-measure confounder U between X and Y. And the second one is exclusion restriction, that Z does not directly impact Y other than through X here. And there is also a third relevance condition, which is essentially the error between Z and X here. However, in this study, we do not require this assumption. Just because, so you can see if we don't have this error here, then we're back to this UXY model, which is essentially an observational study. So all of the results I'm going to be talking about will still be valid. The only difference is whether you will get an informative result or not, meaning that if you have a bound, does the bound include 0 or not? But other than that, all of the results will still be valid. Okay, so there are quite a lot of existing literature in this area. So the first is bounds for binary IV, meaning binary exposure and binary outcome. And when the instrument is also binary, the average treatment effect is partially identified, meaning we have a bound by either the Robin-Maskey bound or the Balke-Pearl bound, depending on what assumption you're assuming. And Richards and Robbins 2014 generalized this to the categorical instrument case with Z bigger than 2. And Swanson et al. 2018 gave a really comprehensive discussion of all of the underlying assumptions and results in all of these different works. And the second strand of work is this falsification test, which is essentially to test whether a given observed distribution is compatible with particular sets of the IV assumptions. As I discussed, there are 3 different assumptions for the IV models. And these different works all focus on different IV assumptions and different types of variables for this falsification test. And there are also other related work. So, for example, in the econometrics world, Brett Samuel, Russell, and Luan Wang, they all look at this problem through random set theory. So another estimate that people look at is this late. So late for binary IV is the effect among compliers, and it can be actually point identified instead of partial identified if you're willing to assume this monotonicity assumption, so no defiers. However, this requires determine whether a subject would have been a complier had they been in the experiment. And this sometimes can be less clear for a policy change just because you need to decide whether they're compliers or not. And for example, in our study, that would mean it requires we know that whether the responding officer would always have judged it according to the assigned strategy, whatever that was. And just because we're more interested in just the intervention effect, focusing on specifically those compliers might not be the best estimate to go. So already said there are a lot of work that's on the binary IV. So the question is, can we just look this as a binary IV? So a lot of times people are interested in pairwise comparison. So for example, if we only want to compare a vice versus separate, can we just drop the first column and only focus on the data with x equal to x in the vice arm or the separate group? And the answer is simply no, because that would mean our estimate is conditioning on the treatment. So conditioning on the treatment is not, the treatment taken is not a rest. And that will make z not independent of y anymore. And this can be actually seen from the stack. So if we condition it on this x here, that basically opens up this path zxu, and that will be a violation of the IV assumptions. So for our work, we'll focus on giving a characterization and partial identification of the generic categorical IV model. Okay, so now we'll talk about categorical, our main result. So we start with the setting. We'll consider a categorical IV model with all of them are categorical. So the Z, the instrument, is taking Q levels. The treatment X is taking K levels, and the outcome Y is taking M levels. And we'll assume the usual consistency assumption, and we assume that independence condition and an exclusion restriction. So our objectives are the follows. First, we want to give a characterization to characterize the set of the counterfactual distribution that is compatible with the observed distribution. And then based on the characterization, we can do a falsification test, as I discussed, that's to test whether a given observed distribution is compatible with the IV assumptions or not. And then after that, we'll partially identify every treatment effects or actually any linear functionals of this joint probability distribution, counterfactual distribution. So you can also do just the marginal probability as well. And lastly, we'll construct confidence intervals for those estimates of interest. So we'll first start with what do we actually mean by our characterization? And we'll start this with, in the case of binary treatment and binary Y, and we'll start with the observational study, which basically means the number of instrument arm is just 1. And it's well known that in the observational study, we have 6 pairs of inequalities that it needs to be satisfied. So 4 of them are on the types, help, hurt, never recover, and always recover. And 2 of them are on the marginal counterfactual probability. And the 4 types are also defined in terms of the counterfactual probabilities, and they're quite intuitive. So for example, for helped, it's basically just saying it's the type of people that they will not recover under control, but they would recover under treatment. And it's similarly for hurt, never recover, and always recover. And if we just draw these 6 pairs of inequality geographically, you would get this picture. So here, the 3 axes are help, hurt, always recover. We have only 3 of them because they add up to 1. So if you know 3, and then you will know the 4th one. And then from these observed probabilities, you can actually construct these 6 pairs of parallel planes so that eventually you look like a picture like that. So characterization basically just means given observed probability. So this is what we can always get from an study. What do I actually know about my counterfactual probabilities? Because the counterfactual probabilities are those things we don't know, and are those things our estimates are built on. So in this case, it just simply means given the observed probabilities, I know that my counterfactual probability need to live in this polytope. And that's what we mean by characterization. So in this talk, we'll just focus on an simplest IV model, M1, with this 3 assumptions. So specifically, we have consistency assumption that's usually seen in causal inference works. And then for that exclusion restriction, we'll assume this individual level exclusion. So that'll say for z and z tilde, y of xz equals to y of x z tilde. And then for the independence assumption, we're just going to assume this randomized assignment assumption that z is essentially independent of everything. So z is independent of all the y potential outcomes and all the x potential outcomes. But in our paper, there are other 4 IV models, M2 through M5, that we considered in, and that's also what people have considered in the literature for various works. And they're defined by weaker versions of this exclusion and independence assumptions, to which our results still apply. And these models may be of interest in testing causal quantum theories in the area of quantum mechanics. So here I'm just showing all of the 5 models that we considered in the paper. So as you can see, besides the individual level exclusion restriction, we also considered joint stochastic and latent. And besides the random assignment for the independence assumption, we also considered joint, single world, and latent variable exogenity. And the relationship between them can be seen in this picture. So here in this talk, we're just going to focus on this M1, which is the smallest and strongest model among all of the 5. So this theorem 1 is one of the main results of our work that gave a characterization of the categorical IV model. So recall we have categorical instrument taking Q levels, categorical treatment taking Q levels, and categorical outcome taking M levels. So this theorem 1 essentially says, under the IV model, M1 through M5, the set of counterfactual distribution is characterized by this set of inequalities. So for each instrument arm, the left-hand side is this joint counterfactual probability. And the right-hand side is this observed probability. And here, VK is just a non-empty subset of M. So the VK is basically defines the range of y of xk. And then we have this condition just to ensure basically we don't get a trivial inequality that this sum up to 1, and that's it. So this might seem a little abstract, and now we'll give a specific example of one of those inequality. What does it look like? Okay, so here, if we just assume we are in a world with a binary treatment and then y taking 3 levels, and we have v of 1 being the whole set 1, 2, 3, and that just means y of x1 can take 1, 2, 3, and we have v of 2 being 1, 2, so that just means y of x2 can take 1 or 2. And this is essentially just will simplify to be like that. And if you just substitute this v1 and v2 in this inequality, and then just take 1 minus on both sides, that will become this triangular inequality. So essentially it's just y of x2 not equal to 3 less than or equal to 1 minus x equal to 2, y equal to 3. If you look at this, it's pretty intuitive and also it's very simple. So the left-hand side is essentially just a linear combination of your joint counterfactual probability. And the right-hand side is also just a linear combination of your observed probability. And similarly, if you take V2 to be 2, 3 instead of 1, 2, that will give you this star inequality. And we can also represent each of the inequality graphically, and depending on different person, it might be more intuitive or less intuitive for you. So let us again focus Z to be an instrument arm, and then binary treatment and white taking 3 levels. So we can construct such a bipartite graph where there is an edge between every pair of the counterfactual and observed values that are compatible under the IV model. So here we have the counterfactual events, and here we have all of the observed events. And just to see how we constructed that bipartite graph, if we start from this observed event, for example, the first one, what are the compatible events on the left-hand side? So here we just know y of x1 need to be 1, and there is no other constraint or other information on y of x2. So that would mean all of these 3 counterfactual events are compatible or obey consistency of this observed event. Coming from the other side, if we start with the counterfactual event, we know when x is 1, y is 1. When x is 2, y is 1. So that would mean these two are the compatible events, observed event for that counterfactual event. So if we do that for all of the events, then you will get to this complete bipartite graph. So back to our example, we have V1 to be 1, 2, 3, and V2 to be 1 and 2. And this was the triangle inequality we saw before. And if you expand it, that's essentially just this inequality up here. So how to see that graphically? It's basically taking V1 and V2, we can just identify the Cartesian products of V1 and V2 on the left-hand side. That will be these 6 counterfactual events. And after that, we're just going to identify what are the compatible events, what are the compatible observed events. That's going to be these 5 events. So now the last step is simply just to add up what's the left-hand side, and that will be the left-hand side of our inequality, and add up the right-hand side. And that will also be the right-hand side of our inequality here. And if we stare at this bipartite graph, this is actually also proves the necessity of our bound, because you can see all of the edges coming from all of the Cartesian product events are included in this inequality, comparing to the full bipartite graph. So this essentially just tells us this bound is necessary. How we proved this theorem 1 is there are 2 parts of it. So first, if we define this mapping phi from this joint probability in model MI, and then mapping to this counterfactual and observed distribution pairs, and if we let T to be the set of right-hand side pairs that obey the inequality in theorem 1. And theorem 1 is just equivalent to the claim that phi of MI equal to T. And there are 2 directions. So the first direction is basically phi of MI is a subset of T. And this essentially shows the necessity of the bounds, which we already saw and is relatively easy to show. So for all the models, it's essentially you can show it by algebra. The other direction is much harder. So that direction, phi of MI, is a superset of T. That shows the sufficiency of the bound. And we show this through a finite space version of Strasson's theorem, which is more user-friendly than the random set theory, but we will omit the detail in this talk. So combining these two, we know that our bounds is necessary and sufficient, and that means it's sharp for all of the 5 models. Okay, so continue our example. This star and the triangle inequality are what we saw before. So if we just simply add up this star and the triangle, that will lead to the square inequality. And this square inequality is actually corresponding to V1 being 1, 2, 3, and V2 being a singleton 2 in theorem 1. So what does this tell us? This actually tells us, even though all of those inequalities in theorem 1 we presented, they're necessary and sufficient, but some of them can actually be implied by other inequalities in the set, which means they're redundant. And to see how that is possible graphically, so some people might ask, why is it also like being necessary at the same time being redundant? So as we can see, assume this blue region is where the true distribution lived in. All of these inequalities represented by the black lines are necessary. So looking at this line, if this line represents inequality defining the area below, this is necessary to hold, because otherwise you would end up being up here, and you will be violating that. So you'll never be in this true distribution here. But this is redundant, because if you already know these two inequalities, that inequality automatically holds. So that's why it can be necessary and sufficient, but redundant. So by characterizing the extreme points and hence all of the facets of the polytope, we can further derive a set of non-redundant inequalities. And that's essentially what our theorem 2 says. So in theorem 2, we're able to characterize a subset of those inequalities by satisfying either 1 or 2, those 2 conditions. So the final set of inequality we have is actually necessary and sufficient, and also non-redundant. And the total number of inequalities we have by theorem 2 is in the order of q times 2 to the times k. And it's much less than what you would have got if you're using our sense inequality, because that will be in the order of q times 2 to the k. So it's increased exponentially in k. And that will be a very large number and increase very quickly if you have a lot of treatment arms. So lastly, I'll just make a note on the falsification of the IV model. So as we saw before, given a set of inequalities, we can have, for one instrument arm, we can have 1 polytope. And our theorem 1 is actually conditioning on each of the instrument arm, which means that the format and the form of the inequality will be the same for all of the instrument arms. So I can do that I can draw a polytope for the first instrument arm, and then I can draw a polytope for the second instrument arm. And if there is empty intersection between the polytopes defining this joint counterfactual probability distribution, then that will simply implies a falsification of this categorical IV model. Okay, and now Richard is going to talk about statistical inference and data analysis. Stop share.
You're muted right now. Sorry, Richard.
Okay, for the next part, we're headed into statistical inference for the model we just categorized. There are at least 2 targets, I believe, for statistical inference. The first one, suppose we care about a bunch of average treatment effects that contrast 2 pairs of the treatment levels. Suppose we have a bunch of those tau k k primes that contrast the effect between treatment level k and k prime. And we wish to construct confidence intervals that cover all those treatment effects. And this is relatively straightforward given our categorization, because every ATE is in fact a linear functional of the counterfactual distribution. Because we just obtained the categorization of the counterfactual distribution as a polytope, we can simply project the polytope along those linear functionals and get tight lower and upper bounds. However, by doing so, we're basically equating the observed distribution with the empirical distribution by assuming there is no error. However, this ignores the sampling variability of the empirical distribution across different treatment arms, which is something we need to handle. The second task is a potential falsification of the IV model. Of course, we start the analysis by assuming there is an underlying IV, but however, if the data strongly suggests to you that the observed distribution does not admit any underlying categorical IV, then we should be able to raise an alarm to alert you that the modeling assumptions probably do not hold. Here it's worth mentioning that for the confidence intervals I'm talking about, these refer to confidence intervals that cover the whole range of population level identified intervals with a prescribed probability. So because we're dealing with categorical data, it's worth considering a classical toolkit for conducting inference for multinomial experiment. Here, for example, let's consider a categorical or multinomial experiment over capital N categories, where xn, x1 through xn are the count, and p1 through pn are the probability vector. Here, I use the p hat to denote the empirical distribution over those categories. By classical Wilks theorem, it says the log likelihood ratio statistic, which is 2 times the sample size, times the KL divergence from the empirical to the truth, as n goes to infinity, will converge to a chi-square distribution with capital N minus 1 degrees of freedom. And this is provided that you hold p and hence capital N fixed and let the sample size tends to infinity alone. So our question is, for our inference task, can we reliably use this likelihood ratio statistics as entire result for statistical inference? Because we're dealing with a case where the sample size may be moderate or slightly large, and we could also have a moderate or a little bit large number of categories. So to illustrate the reliability issue, we can consider the following simple simulation. Here, I simulated 2 types of the true distribution over capital N categories. One type is colored in red, is sparse. That means the mass is distributed only to a few of the categories. And the other colored in blue is dense. That means the probability mass is distributed sort of evenly across different categories. Here, the number of categories would correspond to the number of categories in the domain of instrument, outcome, and treatment multiplied. So it's capital K times capital M times Q, number of categories. And I'm doing this simulation in a regime where I keep the ratio between the total sample size and number of categories to a fixed value 10. So let's start with the sample size equals to 100 and the number of categories is 10. And you can see from both the sparse and dense regime, the likelihood ratio statistic sort of aligns with the predicted Wilks distribution, Wilks chi-square distribution. However, if we make n a bit larger, you will see that the 2 sampling distributions start to drift away from the chi-square distribution in opposite directions. That means we can't really reliably use the chi-square distribution for statistical inference, because it could either be conservative or anti-conservative, depending on the actual shape of the categorical distribution, which we don't know. Also, it's worth mentioning that we learned in introductory statistics that n times a p, like every cell has 5 counts, is good enough for the central limit theorem. However, here we see on average every cell, even though it has 10 counts, is still not good enough for the CLT to be applied reliably. And also, intriguingly, even for the case where we only have 2 categories, ensuring solid coverage in finite-sample for the underlying P is actually a not trivial problem. Okay, so for the statistical inference in this paper, we don't use the aforementioned asymptotic chi-square. Instead, we rely a finite sample result. And that is due to a Chernoff bound that we obtained in the previous paper. The Chernoff bound states that the likelihood ratio statistic, the probability of likelihood ratio statistic greater than an arbitrary value t is going to be bounded by that expression. And the central to that expression is an explicit upper bound, GNK, on the moment generating function of the likelihood ratio statistic that only depends on two things, the number of categories and the number of sample size, which we know. It doesn't depend at all on the shape of the underlying true distribution. So we basically use this result to construct a finite sample confidence region for the underlying observed true distribution. Here is a statement with a pre-specified probability 1 minus alpha, then it holds with probability at least 1 minus alpha that the likelihood ratio statistic is going to be upper bounded by a certain critical value T alpha. Here, because in every instrument arm, there is the data is affected coming from an independent monomial trial. So here, the likelihood ratio statistic takes the form of a sum over different instrument arms. And here, the critical value T alpha can be exactly solved from the Chernoff bound using this expression. What's nice about this confidence region result is that it is finite sample, and more to that, it is in fact a convex confidence region, which is good for running optimization program. And also, if we compare the size of confidence region to the standard parametric confidence region, actually under the regime where P is fixed and the sample size tends to infinity, the confidence region obtained here is going to shrink at the usual parametric rate. So using this result, we can basically conduct statistical inference through a convex program. Here, suppose we're interested in a collection of linear functionals, f1 through fj, such that the average treatment effects, we can construct their confidence intervals, the little L1 use by solving the following convex program. In the program, we have two sets of programming variables. The first set is the PZs, that is the true observed distribution in every instrument arm. And the other one is the P prime, that is the central object that we categorize, that is the counterfactual distribution. So in the program, we're going to obtain the minimum and the maximum for each of those linear functionals, subject to the same set of constraints. And the constraints are given as follows. The first line is just writing theorem 2. It's the set of non-redundant inequalities that categorize our model. And the second one is given by the confidence region presented on the previous slide. And the last two inequalities simply are confining those unknowns to be probability vectors. For the results obtained from such a program, we have the following theoretical guarantee. Under any IV model MI that we consider in our paper with probability at least 1 minus alpha, it holds that all those linear functionals are going to be captured by their respective confidence intervals simultaneously. And furthermore, those confidence intervals are going to be non-empty. Note that this is a simultaneous non-asymptotic result. And furthermore, if any of those intervals from the convex program we obtained is empty, that would effectively raise an alarm that indicates the IV model is falsified strongly by the data. We also have the guarantee that the probability of raising the false alarm is controlled below alpha. Okay, so on the last slide, I'm going to present some data analysis of the Minneapolis Domestic Violence Experiment data. Here I'm presenting the results obtained from the method we developed. Our analysis is based on the full data set, so we are using all the levels of the instrument and all the level of the treatment. Here I'm looking at two specific ATEs. On the left, you have the effect contrasting advice and arrest on the probability of reoffense in 6 months. On the right, the effect is to contrast separation versus arrest. For both of those effects, you can see two bounds. The narrower one are the plug-in bounds by treating the observed distribution to be the empirical. And the wider one are the nullified confidence intervals that we obtained from the convex program on the previous slide. So indeed, if we just focus on the plug-in identified intervals, we see that those effects seem to be positive. That aligns with existing finding in the literature that claims that arrest seems to be the most effective strategy that minimizes, that reduces the chance of reoffense. However, if we seek significance, unfortunately, both of those confidence interval cover 0. That means those effects are perhaps not significant, and particularly on the effect of the left, where if it is indeed significant, that would require a much larger sample size to reveal the significance. It's worth mentioning that the two confidence intervals, they hold simultaneously with 95% coverage. And also, this is very fast to run on a modern computer. It takes only a few seconds to run, and in fact, the size of the linear program is moderate in the sense that the number of IV inequalities in that program is 78, which would be much smaller than the number of inequalities if you apply Arstein's theorem from the random set theory. So the next few bounds come from a different analysis that if you delete a certain level of the instrument and you keep all the levels of the treatment, for that you obtain those bounds depending on how much information of the instrument you delete about the effect. Typically, you get a bound and a confidence interval that is going to be wider than the bounds obtained from our method. And so I guess the message here is using more instrument arms can improve the efficiency of those analyses. And finally, as far as we know, I guess prior to our paper, there hasn't been a really applicable result that give you the bounds for an instrument when the treatment takes more than 2 levels. So if you try to do a Procrustean analysis by pretending the IV, even if it has 3 levels, it is made into 2 levels by deleting a certain level of the treatment. Those are the bounds you obtain. And as we argued previously, this is unfortunately biased. And also we see it is entirely unnecessary because these bounds, not only they are biased, they are only a tad bit smaller than the bounds we obtain using our sound result. So the message here is, I think it's no longer necessary to use to pretend you have a binary IV when in fact you have more than 2 levels of treatment and instruments. And with that in mind, I thank you all very much for your attention, and I very much look forward to Professor Kidani's discussion.
Yeah, thank you so much for the talk. Just a brief point. I think Jingwan had a quick question that we could take before we switch over to this discussion.
Yeah, sure. I had a couple of questions actually. But one question is about this inaccuracy of the chi-square test. Is that related to these results about kind of testing like chi-square test for logistic regression in high dimensions? Are you familiar with that, Richard? Is there like a connection to these results?
I'm not too sure there's an explicit connection, but the phenomenon are kind of similar in the sense that in a different asymptotic regime, the asymptotic distribution or the approximation of the chi-square could be debatable, I think.
Okay. And my second question is about this convex program you have to get confidence interval. Can you say a little bit about that, how easy it is to solve it? Because it's not a linear program.
Yes. Yes, this is not a linear program indeed, but it is still a convex program. So what the constraints define is basically an intersection, if you wish, a polytope and a convex body. and we are basically obtaining the maximum and the minimum of a linear functional of that intersection. So it's a convex program, and because we obtain a smaller number of inequalities, so for, I guess, kind of the moderate numbers of the levels of the instruments and treatment and the outcomes, this is totally doable on a personal computer with very fast time.
You just plug it in into some like standard off-the-shelf optimizer?
Yes. We basically use Gurobi, I think, for solving this, but there are other solvers you can totally use.
Okay, thank you. In the interest of time, let's move on because you've answered all the questions that came up. So let's move on to the discussion.
Okay, let me. Okay, can you see my screen?
Yep.
Yes, it's perfect.
Okay, yeah. Thank you very much for the opportunity to discuss this paper, this fantastic paper. So I will start by kind of summarizing the model and the assumptions, and then give some comments and questions. So yeah, the paper considers the potential outcome models with a categorical outcome, categorical treatment. The outcome is Y, the treatment is X, and then the instrument is Z. They all can take multiple value, okay, discrete. So then it satisfies the Y variable satisfies the potential outcome model, which embeds the consistency assumptions here. When the instrument is assigned to a little value Z and the treatment little value X, then we observe the potential outcome Y of X and Z, okay, in the data. And similarly for the treatment, we have the potential treatment when the instrument is assigned the value Z. So for this talk, I'm going to assume that we have three valued treatment, just to keep it simple, okay?
Do we have a connection issue?
Yeah, I think so.
Looks like it's, yeah. So discussing is frozen at the moment.
Okay, yeah, we can wait a few seconds. As a backup, Aditya, do we have the slides? So we could maybe even go to his questions, I don't know, and discuss them. If we have the slides, I don't know.
So I don't know what happened. It's like
I know, I think he's back.
Yeah, he's back. I think there was some connection issue.
Okay.
You can
oh,
share it.
sorry. Yeah, so something happened. So I need to share my screen again.
Yeah.
Yes, please.
Okay, sorry about that. Can you see my screen now?
Yes.
Yes, we saw the first slide, then I think you were gone after that.
Okay, sorry about that. So yeah, I was talking about the joint stochastic exclusion restriction. The instrument can still affect the potential outcomes, but not the distribution, the joint distribution of the potential outcome, including the Z, is the same across the values of Z's if we are changing Z. So that's weaker than the individual level exclusion restriction. And then we have the latent stochastic exclusion restriction, which states that condition on some unobserved variable U, the distribution of the potential outcome for Y, X, Z is the same as Y, S, Z tilde. And then we have the different version of independence assumptions. The most common assumption that we have is the random assignment. So when you randomly assign the treatment, the instrument is independent of the vector of the potential outcomes and also the vector of the potential treatment, okay? and which is stronger than the joint independence, where you only focus on the vector of potential outcomes. Now, the single word independence is also a weaker version of the random assignment. Now, you're only looking at the potential outcome at the given values of the instrument and the treatment, and then the potential treatment specific to that potential outcome. Okay. And then the latent variable independence. So the paper considered the 5 versions of these IV models. The M1 is the strongest one, the individual level exclusion restriction plus random assignment. Okay. So the first result that I think is important in the paper here is that they characterize the distribution for the potential outcome, okay, the joint distribution for the potential outcome under these 5 models. And they found that the identified set is the same under these 5 models, even though some of the models are weaker than the others, and some of them they overlap. Okay, and they propose sharp characterization of these identified sets, which I think is a main contribution here. And you can have this identified set, but then you have a lot of inequalities. So what they do, they propose a way to eliminate redundant inequalities. Indeed, you usually have a lot of redundant inequalities. So if you reduce the number of redundant inequalities, then it makes inference easier, and also the characterization of the parameters that you care about simpler. And they propose an inference method for the bounds of functionals of the bounds. Okay, so I think this is a very nice paper. I very much enjoyed reading it. The main theorems that I find interesting and I will focus on are related to the first part of the talk, theorem 1 and theorem 2. I also like the inference part in the linear programming representation, but I'm going to focus my talk on the theorem 1 and theorem 2. Okay, so the paper shows that under model 1 to 5, all these 5 models, we have the same identified set for the joint distribution of the counterfactual outcomes. Okay, so my question is this characterization sharp under all models? So based on my reading of the paper, it seems like the answer is yes. Okay, but then here's the question I have. So how about the restrictions that the model 1 imposes on the joint distribution of the potential treatments? Like if I care about the strata, okay, the types, the compliers, defiers, always takers, never takers. The model 1 imposes some restrictions on this joint distribution of the potential treatment, which are stronger than the one that you get under assumption 4, for example. So the model can be, I can have an identifier set that is sharp for a given parameter, but when I change the parameter of interest, one of the models can give me tighter identifier set on that specific parameter. So the question is, what we need to kind of give some nuances about when we say that these 5 models they provide the same identifier set, because it depends on the parameter that you are looking at. So I think it's important to highlight that. So if I care about if the local average treatment effect is my parameter of interest, I believe that model 4, which is the swig one, the single word independence, does not provide a lot of information about late. But model 1 can give me sharp identifier sets on the for the late, for the compliers and defiers. And in the paper with some of my students, we kind of provide the sharp identifier set for the late under model M1, but M5 and M4, they will not give you the same identifier set. Okay. Now, theorem 1 is great and has a lot of implications, and I like that. For example, model 4, which is the single word independence, it shows that you will have the same testable implications for the IV models that I look at in the paper with Ismail and Kirani and Murifié. So we derive what we call the generalized testable generalized instrumental inequalities under the joint independence model 2. But here the paper is giving it an implication that also implies the same set of generalized instrumental inequalities that we derive under the joint independence, which I think it's a nice result to say that, okay, these generalized instrumental inequalities, if you think about the Peirce inequality, the Bonus inequalities, the Kidani-Murphy's inequalities, you can also derive them under this single word independence assumption, which I find cool. And that's a kind of a nice result. And I think it's you can highlight that in the paper. It will be an addition. Now, you can actually derive from Theorem 1 all the generalized instrumental inequalities that we derive in our paper. And even if the treatment is multi-valued, right, and you don't restrict the dimension of the number of values that the treatment can take, and also the instrument can be anything. It can even be a vector. So you can derive the generalized instrumental inequalities that we have from this Theorem 1. I show that here. I will not spend time on that for the interest of time. But basically, when you take Theorem 1 and then you just marginalize, you take the one of the set to be equal to the support the real line, you get some implications. And then if you just rearrange things, you get the generalized instrumental inequalities. Okay, so that's kind of interesting. Now, the question that I have is, can we do the other way? I can start from Theorem 1 and get the generalized instrumental inequalities. But can I start from generalized instrumental inequalities and show that they are sharp with respect to the model 1, model 2 to 5? So it's like, if you give me Theorem 1, I get the bounds on the joint distribution of the potential outcomes. From there, I can derive the generalized instrumental inequalities. But can I show that these generalized instrumental inequalities, now they are sharp? Because I don't have any additional instrumental inequality from this Theorem 1, which we know, right, from your proof that you have a sharp characterization. So this characterization is sharp. And then it yields the same testable implications that we have. Can we prove now that these generalized instrumental inequalities are sharp? I think that's an open question. I am very much interested in that. Now, suppose that I only care about the ATE in your framework, okay? And I don't care about the joint distribution. So take the case where the treatment is binary, but the instrument can be multi-valued, like 3 in your example, in your empirical example. In Kidani-Murphy, we derive bounds on the marginal probabilities, right, of the potential outcomes. So the ATT can be just the difference between these two probabilities here. Okay, so my question is, the bound that we get from taking the difference of these bounds here on the marginal probabilities, if you don't look at the joint distributions, the one that you get when you consider the joint distributions, are they tighter than these ones that we get here? At least on a numerical example, or maybe in an application, if you compute the sample and or you forget about inference, do you get tighter bounds than the one that we get if we just take the difference from these bounds here? Okay. So I like the result on the elimination of redundant inequalities very much. Usually, this characterization in Theorem 1, it leads to a lot of inequalities, and many of them, they are redundant. So I think providing a way to eliminate redundant inequalities is very important for identification and also for inference. And I like that. But there is a recent paper by Luo and Quarters where they also propose a way to eliminate redundant inequalities. And I think it will be important to highlight the difference between the two papers. I think you use some bipartite graphs and result, they're also using that. So it will be important to highlight the difference between the two. But I think all in all, I think I enjoy reading the paper, and thank you for this fantastic paper.
Yeah, thank you so much for the great discussion. Yilin and Richard, do you want to respond?
Yeah, in light of time, I can just quickly respond to some of the questions. I guess the answer that all the models we consider, they have categorization, yes. And also, you mentioned something, basically, I guess there is subtlety here. We consider 5 types of model, but not all of them assume X counterfactual Z. So for your question about, those compiler types and such, I think because we focus on kind of the commonplace for all the 5 models, we didn't really investigate that one, but it's certainly of interest. On the Law M1 paper, we reference to a previous paper from Law and the last author, and we discussed the connection in our supplement. But thanks for pointing us to the newer paper from Law et al. We will definitely take a look. Yeah, I think your question about the generalized instrument inequality, I guess, yes, it can be derived from theorem 1. But your further question, I don't think I have a good idea, but we can save that later for offline discussion. But thanks again very much for a very insightful discussion.
Thank you.
Thank you.
Thomas has something to say, I guess.
Yeah.
No, I was just sorry. I was trying to applaud. I wanted to thank Desiree for a great discussion. That was all.
Thank you, Thomas.
Awesome. Thank you. Okay, I think we're at time, so I'll quickly wrap up. So first, thank you so much, Yilin and Richard, for a great talk, and Desiree for a very insightful discussion. Next week, joined with the Isaac Newton Institute, we will have Paul Rosenbaum from the University of Pennsylvania, who will talk about unmeasured bias in observational studies. We're very much looking forward to the talk. Just a quick heads up. Next week, we're going to start half an hour earlier at 8 a.m. PT. So we'll again write it also in the email, just something to watch for. Thank you all for coming. I hope you have a great week and see you next time.